Welcome to this explainer. Today, we're going to take the dense, honestly, sometimes overwhelming world of chemical kinetics and transform it into a fast-paced, cheat code masterclass, specifically designed for the IIT JEE. Seriously, if you've ever stared at a reaction rate equation and wondered how it actually connects to the real world, or you just want to instantly spot those tricky traps examiners love to set, you're in the right place. Let's get right into it.
Okay, so first things first, we need to nail down a foundational distinction. Think of it like this. Chemical thermodynamics is the ultimate judge of possibility. It basically tells you if a reaction can even happen at all. But chemical kinetics is entirely about speed. It doesn't just ask if the car can drive, it asks, how fast is it going, what's under the hood, and how can we push the pedal to the metal.
So here is our definitive roadmap for today. We'll be covering 1. The need for speed, 2. Turning the chemical dials, 3. Order versus molecularity, 4. Zero and first-order math, 5. Heat and the Arrhenius equation, and finally, 6. Collision theory and pro tips. All right, Section 1. The need for speed, defining the rate of reaction.
Simply put, the rate of a chemical reaction just measures how things change over a specific unit of time, and we measure that in moles per liter per second. Now, when you look at the math for a standard reaction, you are going to see a negative sign used for reactants and a positive sign for products. Why is that? Well, the negative sign indicates how fast the reactant concentration is decreasing or disappearing, while the positive sign shows how fast your shiny new product is increasing. It's exactly like your fuel tank going down while your speedometer goes up. It's really just a matter of perspective.
Now, there's a super important distinction to make here between an average rate and an instantaneous rate. An average rate looks at the big picture, right? It's the change in concentration over a long, specific time interval. But the instantaneous rate, that is like taking a photograph with a high-speed camera. It captures the exact, precise rate of reaction in one single split second.
Moving on to Section 2, turning the chemical dials, factors affecting reaction rates.
There are 5 major factors. Think of them as literal dials that we can turn to dictate speed. Turn up the concentration and you get more collisions. Turn up the pressure for gases and you're physically forcing those molecules closer together. Add a catalyst and you provide a completely different, much easier pathway for the reaction. And the best part is it does this without permanently consuming the catalyst itself. And then there's surface area, which is a massive one for solids. For example, if you have powdered zinc, it's going to react much faster than large, chunky zinc granules simply because there are just way more exposed particles ready to mingle.
And speaking of these dials, here is a massive rule of thumb for the temperature dial. In kinetics, 10 is literally a magic number. Generally speaking, for every increase of 10 degrees Celsius, the reaction rate doesn't just bump up a tiny bit, it actually becomes about 2 to 3 times faster. We are talking massive exponential increases in speed here, because a higher temperature means higher kinetic energy and significantly more effective collisions. This exponential jump is exactly why keeping your food in a cold refrigerator stops it from spoiling. We are quite literally freezing that kinetic energy in its tracks.
Let's hit Section 3, order versus molecularity, avoiding the classic exam trap.
Now, this is where people get tripped up all the time. The absolute crucial point to remember is that molecularity is purely theoretical. It simply counts the reacting species involved in one single elementary step. And because you obviously can't have half a molecule colliding, molecularity is always a whole number, and it is never zero. The order of a reaction, however, that is strictly determined by real-world experimental data. It applies to the overall reaction, and it can be zero, fractional, or even negative. So whatever you do, never confuse the theoretical counting of molecularity with the messy experimental reality of reaction order.
All right, Section 4, zero and first-order math, the ultimate cheat sheet. The absolute most heavily tested math you're going to face involves zero and first-order reactions. Let's break it down. For a zero-order reaction, the rate is entirely independent of concentration. It just equals the constant K. But check out its half-life. It does depend on the initial concentration. Now contrast that with a first-order reaction. It's the exact opposite. The rate depends on the concentration, but its half-life, which is 0.693 divided by K, is completely independent of its initial concentration. This is exactly why things like radioactive decay, which follow first-order kinetics, have a constant half-life regardless of how much material you actually start with. You definitely want to take a second to really lock these relationships into your memory.
On to Section 5, heat and the Arrhenius equation, connecting temperature to speed.
Before we look at the exact calculation, we really have to understand activation energy. Think of activation energy like a physical hurdle on a running track.
It is the absolute minimum energy required for a chemical reaction to even happen. So a higher activation energy means a much slower reaction simply because it's a taller energy barrier for the molecules to clear. And remember what we said about catalysts earlier? When you add a catalyst, you aren't somehow giving the molecules more energy, you are magically lowering the height of the hurdle itself.
So this right here is your master key for temperature problems. When you're faced with two different temperatures on an exam, the two-temperature Arrhenius formula is exactly what you need. You plug in temperature 1 and temperature 2, and you can instantly crack the unknown rate constant, or solve for that activation energy hurdle we were just talking about. Seriously, memorize this exact layout. Having this formula locked and loaded is going to save you vital minutes on test day.
Finally, Section 6, Collision Theory and Pro Tips, Why Reactions Happen.
According to collision theory, molecules are constantly crashing into each other in this chaotic, microscopic demolition derby. But, and this is a big but, not every crash actually results in a reaction. To form products, you need what's called an effective collision. And an effective collision demands two things to happen simultaneously. Sufficient energy, meaning they have to hit hard enough to overcome that activation energy, and correct orientation. They have to hit each other at the exact right angle. If they just graze each other, or if they hit backwards, they just bounce right off, and it doesn't matter how fast they were going.
To wrap this all up, let's lock in some rapid-fire tricks examiners love to use to trip you up. Ready? Remember, molecularity is never zero or fractional. A catalyst lowers activation energy, but it absolutely does not change the equilibrium constant. Turning up your temperature dial increases the rate constant K, but it does not change the experimental order of the reaction. And lastly, you can almost never just look at a complex balanced chemical equation to find its rate law. It has to be determined by real-world experiment based on its slowest step.
Well, that leaves us with a pretty fascinating final thought. You now basically possess the blueprint to manipulate chemical time itself. You understand the hidden dials, temperature, surface area, catalysts, that control exactly how fast the microscopic world operates. So if you could harness this knowledge outside the exam room, which real-world reaction would you speed up to save the day, or maybe slow down to buy humanity just a little more time? Keep that in mind as you study, and I'll see you in the next explainer.